Hello, everyone. Welcome to Innovating to TechTalk. Today, we are happy to have Dr. Kelvin Orr, Associate Professor and Assistant Head of Department from Department of Industrial and Manufacturing Systems Engineering to be our moderator. Without further ado, Dr. Orr, please.
Thank you. So good afternoon, everyone, and welcome to this Tech Talk. I'm Kelvin Orr, the moderator of today's event. It is our honor to have Professor Ning here next to me to deliver a Tech Talk today for you. So Tech Talks is a series of forums and dialogues given by engineering researchers of diverse academic backgrounds to share their insights on innovation-related topic. The Research Student Series is a new series and delivered by current research postgraduate student as well. Now, the topic of Professor Shi's talk today is wearable assistive robots for aging society. Professor Shi is a chair professor of robotics and automation at the Department of Industrial and Manufacturing Systems Engineering. He is also the director of Advanced Technologies Institute. Professor Shi received his doctoral degree in systems science and mathematics from Washington University in St. Louis, Missouri in 1993. Before joining the University of Hong Kong, he was a university distinguished professor, the John Ryder Professor of Electrical and Computer Engineering, and Director of Robotics and Automation Laboratory at Michigan State University. His research interests include robotics, manufacturing automation, micro-nano manufacturing, nanosensors and devices, and intelligent control and system. Without further delay, may I pass the microphone, invite Professor Shi to the stage for the talk.
Okay.
Thank you.
Thanks, Dr. O. Oh, good afternoon. So it's my great honor to be here, and thanks Innovating to give me these opportunities to present our work. So basically, we're talking about how the wearable robot can help us to face the grand challenge of the society, the aging problem. Okay, we know rapid aging is one of the grand challenges, right? By 2030, right, 1/4 of the Hong Kong people will be over 65 years old. Okay, so there are many reasons, because one of the, it's actually is a good thing, right? Because our lifespan gets longer because of technology, medical service, or the living condition and the environment. Okay, but in another side, there are a lot of older people in the society, right? That cause some problems, right? Because older people usually they have like a mobility problem, manipulability problem, a health problem, right? So how to provide the elder people with a healthy aging, and at the same time provide them with opportunity to make a contribution to the society. I think that is a very important, okay? But the problem, the aging is one of the biggest issue is the mobility and the manipulability problem. The elderly, one of the problems they're facing is a rapid losing of their muscle. Okay, but when you over like 40, every year in average, 5% of your muscle will be gone. Okay, so if you don't keep exercise, don't like pay attention to the nutrition, the process will be faster. Okay, so this kind of problem called a sarcopenia. Okay, but once you lose a lot of muscle, right, then you get weaker, right? Then you will have a mobility problem and the manipulability problem. Okay, that will like create a lot of difficulties in your daily life. Okay, see the CDC, the U.S. a government agency about the disease control, right? They did a study, okay, for the people over 65, 1/3 of them had a problem of falling, okay? Because they have a weak muscle, right? They cannot support the body properly, right? They fall, okay? So that means every one of the 3 elderly over 65, they had experience falling. Okay, then among them, 1/3 of them, right, had a severe damage, right, like a bone fracture, damage to their head, right? Some of them became permanent, right? Some elderly, once they fall, they break their bone, then they never recover. Okay, so all those kind of problems, right, are facing the elderly people. Okay, then the question is, how can we develop technology to help them, right? To help them to improve their mobility and manipulability. Okay, so we believe wearable robot can be one of the solutions. Okay, actually, for last 20, 30 years, people have been developed this kind of technology. So you can see these are some of them assistive robot, right? Some called the exoskeleton. So basically you wear the robot, right? Robot will help you to move your leg and move your hand in order to provide certain mobility and manipulability, okay? But you can see those kind of robot usually very bulky, right? Has a rigid structure, okay? And but recently, people also introduced the technology called soft robot, okay, in order to improve the wearability, because then basically the structure of robot is not rigid, right? Made of the fabric, all those kind of things, so you can wear it more comfortably. But this kind of device, most of them use for rehab, okay, because you have a very bulky driving system, like battery, all those kind of things, right? So it's very difficult to carry it on, right? To use it daily, okay? So then, see, we can look at the existing system, this kind of assistive robot, actually in the 2 different streams, right? One, we talk about those exoskeletons, that's for performance enhancement, okay, not for the elderly, even for young people, you wear it, right? You can increase your like a capability, you can carry more heavy load, and you can like jump higher, all those kind of things, right? For enhanced performance, okay. But then in another end of extreme, right? For the like parallel people, right? So those people, they completely lost their mobility, cannot move at all, right? Then they use robot to replace their original mobility. Okay, so basically you can think that that's just like a car, human look car, right? To carry those parallel people around, okay? But we are talking about the assistive device is something in between, okay? Because for those elderly, even they lost significant amount of muscle, they still have some muscle left, okay? So then they don't want robot to replace their muscle. They want the robot to help their muscle, right? But not enhance their original capability, right? But to assist them to recover, right? Regain their mobility. Okay, so that's why it's something in between. This is very important, okay? Because the reason is the muscle, right? If you use some devices, right, to replace muscle, without using the muscle will be gone faster, okay? That's why exercise is very important. So we want the robot to help the muscle to regain some capability, but at the same time, you still be able to use the original muscle. So this way is very helpful to slow down the sarcopenian process. Okay, so then from here you can understand actually performance assistance is very difficult, right? One of the reasons is for each person, the amount of sarcopenia, the amount of muscle loss is different, okay? So the solution will be personalized, right? So each person will have a different need. So before we give them the robot to help them, we have to exactly identify what's needed, right? We need a personalized solution. Second is, has to be precise. Okay, as I said, the robot will assist the muscle, not replace. Okay, if you overdo it, the muscle will lose faster. Okay, but if you underdo it, right, you will not be able to help him enough, right? So you have to find the right amount, has to be very precise. So that's why this very challenging problem. Okay, so that's challenge we're facing. So from here, you can see, right, in order to solve this problem, we have to develop a wearable robot, which is precise and personalized. Okay, so in order to do this, we develop so-called the UC3 approach, user-centric co-creation. Okay, so key is answer that two challenges, precise and personalized. Okay, see, first we have to identify where the problem is, right? Because human, like mobility, manipulability, come with a 3 different levels. First is like a behavior level, right? So when people doing daily life, right? You walk, you run, you pick up things, you like open the jar, so put the clothes on. So those are behavior based. But in order to perform those kind of behavior, you need a certain function. Your joint has to move in a certain angle, right? Your arm has to have a certain force, right? So those function capabilities support those behavior. Okay. Then the next level is in order to gain those, in order to have those functions, you need a muscle, right? So muscle move your bone to generate to generate those functions. So those we call the physiological level. So all the activity, all the behavior human have, right, to generate by these 3 levels. Okay, see traditional way, so you can see even like performance enhancement or performance replacement, they are concentrated on what? Behavior level, right? You want to move for the handicapped person, you cannot, right? I give you a robot to carry you around, right? So this is a behavior-based approach, right? But this kind of problem is, like I said, right, cannot help you, right, access your muscle, right? Cannot only work for the paranoid person, right? For elderly, will not. Then the function level, right? You can put the robot on your knee to move your joint angle to make it work. But the problem is much more difficult because think about it. Our every joint is not have a fixed axis. When I turn my arm, the axis actually is changing. It's not like a motor. When motor turns, the axis is always at a fixed direction, right? Then people say, oh, you can now move your arm. I put the motor there, I'll help you. But while it helps, it forces your arm joint to rotate it around a fixed axis. Actually, that will damage your joint. Okay, so that's why the function level or behavior level will not fully compensate, will not fully provide the necessary assistance to the elderly. We have to go down to the physiological level. We have to find out which muscle is weak, how much compensation we need to provide. So this way we use the muscle to move the joint, eventually improve the performance, right? So that's the approach we're going to take. But from here, you can see in order to do this, first we have to identify where is that weak muscle, right? So how to model that, then how to determine the proper amount of compensation which is needed. Okay, so all of this is built on like a diagnostic or testing and evaluation. Okay, so before we do that, So actually, we conduct, right, large number of subject testing in Hong Kong. So far, we already test over 150 people, elderly. Okay, we have certain criteria. We test them what kind of performance level, what kind of deficiency they have. So what's the functional level deficiency? What is the physiological level deficiency? Okay, by understanding that, then we can build a model to tell us how to compensate those muscles. Okay, so for each elderly, we actually conduct 25 tests. Okay, it's very thorough. So the whole test over like 4 hours. Okay, so through this test, we can find out where the problem is. Okay, so once we do that, right, then we can develop a model, compensation model, right, which will tell us which individual piece of muscle need what kind of assistance. Then we develop a robot, right, to help that muscle, right? From here, you can see the key is once we understand where the problem is, the next thing is we want to develop robot, not help joint, not help the movement, help muscle. Okay, so that is the key. We want to compensate at the physiological level. Okay, but in order to do that, we have to first understand how the human muscle working. Okay, then you can develop artificial muscle to help the human muscle. Okay, so it's very interesting. So we can see human muscle has a very complex structure, right? Each muscle has a muscle unit divided by different like a component, but for each muscle unit has thousands muscle fibers. Okay, the structure of a fiber actually is quite simple. So from here, you can see all the muscle fiber consists of 2 pieces. One called the actin, one called the myosin. Okay, so the actin and the myosin actually they contract, move with respect to each other. Okay, the reason they can move is they are small, like a piece here called a cross bridge. Cross bridge is like a key. Okay, so like a piece, it's banded to the actin. Once it's banded, right, then it starts moving. Okay, once it's released, it go back. Okay, so you have thousands of this kind of, see, for each fiber, the movement is very simple. Just contract, then extend. Okay, but you have thousands of them. Okay, you can control each individual muscle unit. Then you can generate very complicated movement. Okay, so from here, it will give us 2 like hints to develop artificial muscle. Okay, first one is you don't want to have one driving unit. You have a multiple of them. Okay, so then from the multiple simple movement, you can combine them, you can generate a very complicated movement. Okay, second is our muscle. See you always can see the muscle itself. When we relax, muscle is very soft. Okay, but when you apply the force, muscle gets stiff. Okay, you always like that, right? Because people see, oh, I'm very strong. You can touch my muscle, became very hard. So the stiffness of a muscle is changing. Okay, it's not like those skeleton, the structure always rigid, right? Even without using it, it's a very rigid structure. So that's why it's so difficult to wear. But the muscle flexibility is changed. So we have to develop some actuator, right? Which consists of a multiple simple unit to generate a very complicated movement. And the second is it has to have variable structures, a variable stiffness. Okay. So in order to do this, but the traditional actuator cannot do this. You use motor, so all those things, stiffness, elasticity, always like a constant. Okay. So we have to looking for new material to do this kind of thing. Okay. So that's why we use so-called the material called STG, shear stiffening gel. Okay, this is very interesting material. So when you see, when you apply the small force, it's very soft. You see, the thing is, you can go down easily, but your finger can get in very easily. But you hit very hard, suddenly became very rigid. Okay, so the stiffness of this material will change based on how much force you apply to it. That's exactly the property of the muscle. Okay, so then we use this material to make a fiber very similar to the muscle fiber. Okay, you twist it, right? When you apply the force, it gets stiff. Okay, then the efficiency, the transmission of the force is increased, right? And also elasticity increase. Okay, then you can apply more force. Okay, but when you without force became very soft, you wear it very comfortably. Okay, so that is the material we use. So then we did a bunch of tests. So you can see this is the stiffness of the muscle. Okay, there are some like heuristics, right? Because the muscle you go up and go down, they're different. Okay, so this is the material we use. Okay, STD twist actuator is very similar to muscle, human muscle. Okay, and also this is the tension transmission rate. Okay, so this is for the human muscle. Okay, so this is the artificial muscle. They are also very similar. Okay, so then using this, the next question is how to control them. You have because the muscle, you have 1,000 of them. Okay, you put them together, you became the muscle. Okay, so there are two ways to control. One called the read coding. So your neural system send a pulse to the muscle, right? When the frequency increase, it contract more. Okay, so the higher frequency, the more it contract, generate the bigger force. That's for the individual fiber. Okay, then there's another thing called recruitment. You have a lot of muscle unit, right? Based on the force you need, you will recruit a different number of the unit, right? By combining these two, right? See, this is one fiber, you can keep increasing, but once you read, saturate, the force cannot increase anymore. You recruit another fiber, right? Then they increase. So that's how you generate this force curve, okay? So we can use the same principle to control the artificial muscle. Okay, so this is the artificial muscle we developed. Okay, you can see there are 4 strings inside. Okay, you can consider this like a 4 muscle unit, right? So you can increase the speed like a read coding, the force will increase. Okay, but at some point it saturates. Then you can recruit another one, right? You do the same thing, you generate the force curve. It's very similar to the human muscle. Okay. Okay, then this is the one actuator, right? It's like a piece of the muscle. We already see how it generates the force, but the muscle actually, besides generating force, also has a sensing capabilities here. See, this is the muscle. Then this part called tendon, right? Tendon is the part that connects muscle with the bone, right? Within the tendon, there's unit called Golgi tendon. Golgi tendon actually is sensor, sense the stress. Okay, so that's how can keep our balance. You apply certain force, right? Then you can generate a certain like movement, all those kind of things, right? So those force, they are close loop control there. The force is measured by the force sensor inside the tendon called the Golgi tendon. So we do the same thing in our muscle. So you have fat fiber, right? Then in the tendon, right, we also put a sensor there, right, embedded into the tendon, right, which can do the force sensing. Okay, so this is the sensor. Sensor is like a gel. This we develop. Use some special material. When you pour it, okay, you can actually measure the force. When it deforms, also you can measure it. So this sensor measure both force and the deformation. Okay, so it's very similar to the Golgi tendon. Okay, then we integrate them. So then the next thing is you have to how to control it. You have an actuator, you have a sensor, then you integrate them together. But the human muscle is controlled by some central neural system. So that's how the human sensor motor system works. There are 3 levels of sensing. The lowest level is a proprioceptive sensing. Okay, this does not go through your brain, right? It's like a local feedback loops. Okay, then you have a interoceptive and the extroceptive. So all those sensors, it goes through your central neural system. Okay, but see the traditional way to do the assistive robot is they put the robot there. The robot has its own system, own control system, right? Then you hope your own control system can work with the central neural system, some kind of cooperation, right? Integration at a higher level, but that's much more difficult, right? Because a lot of sensor and also the timing, the scale, all those things is different. So that's how it created a lot of problems. But our idea is we use artificial muscle because that structure very similar to the human muscle. We actually put together with the human muscle, okay? But still use your own control system to control it, okay? So this way we call it a proprioceptive control, okay? So since the robot has actuator, has a sensor, but that will integrate with the muscle sensor and the muscle actuator, but controlled by the same control system as human muscle. Okay, so this way is much more easy to control, to achieve coordinated operation between your own muscle and the robot. Okay. So this is the tested result. See, we developed this robot to assist the muscle called the GL muscle, actually below your lower leg. Okay, this muscle is very important to keep you balanced. Okay, a lot of people, that 2 pieces of muscle has a problem. It's very easy to fall, because that control your ankle movement, right? Then keep your body balanced. Also help you walking. When you walk, right? See, you see some older people, they cannot move their leg. They walk like this, right? Because this 2 pieces of muscle, right, is weaker. Okay, so then we use this muscle to help. We use this artificial muscle to help GL muscle. Then we did some testing, right, to test the ankle, the force generated by your ankle. Okay, see, you can see this original force curve, right? Then we put artificial muscle there, but controlled by the same control system, right? Same the human control system. Then after compensation, the force became this. Okay, so you can see their increment. So that part actually generated by the robot. Okay, so this is like a function level testing, how much your ankle can generate, how much force. Okay, also we did the behavior level testing. Behavior level is what? Because as I said, GL muscle keep your body balanced. Okay, so we have this balance testing. So this device, you stand on it, which can measure the movement of center of gravity of your body. Okay, so before that, you can see the center of gravity move very rapidly. So that means the person is like swimming. Okay, but after we put, because the muscle is weaker, okay, then after we put the robot on, so you can see center of gravity move in very small range. Okay, so from here you can see the muscle actually help stabilize your body. Okay, so then that help you at the behavior level. Okay, so but the key is the muscle actually controlled by your own control system, work together with your original muscle. Okay, so this is besides this robot, at the same time, we are also develop robot to assist the knee, right? And also assist the upper leg, and also your hand. Okay, so we are, but the similar kind of principle, right? This UC3 approach applied to this robot development. Okay, at the same time, we ask like elderly, right, from the community to test our robot. So far, we already test 11 peoples. Okay, the response are very good. Okay, so we are not just test the physical performance of the robot, also test their subjective opinion, right? Like user friendliness, how they think about the robot, also all those kind of things. Okay, we think those things are very important, right, to help us design the robot, right? Because the purpose is to help elderly people, right? So their opinion is very important. Okay, so so I think I pretty much take all my time. Okay, so let me summarize what I tried to say. Okay, there's three key points. The first one is we developed this so-called UC3 approach, which is different from traditional way to develop robot to help people. Okay, so we think that's very important because we are talking with Dr. O about ergonomics. So ergonomics basically is a science or engineering field studies the relation between human and the machine, right? It's a very old field, right? But the beginning is study tools, right? How to design a tool is easy for human to use, right? Then later on, right? People just not just use tool, people have the machine, right? Then the field became study how you design machine to better work with human, right? Now we go one step further. Ergonomics became what? To design machine for people to wear, right? You start with a tool to use, then use a system to work with. So now we want to develop the machine, people wear it, right? How to design machine you can easy to wear can help you. Okay, I think that's very important. So from the scientific or the engineering point of view, it's very important. And the second is this assistive robot, very important to the society, right? Because everybody, you all have like parents, grandparents, right? You have elderly, right? You are responsible to help them. And also the one day, any one of us will get old. Okay, so this technology will impact everybody, right? Everybody will have chance to benefit from it. It's very important, right? Then the third is the technology will create a new economic growth point. People call this silver economies, right? Because there are more people, elderly people in the world, in the society, right? We need to provide them with the technology. They are like consumers, right? So that will create a new opportunity to grow the economy, right? So all of these are very important, okay? So then at the end, I want to say, see this project that I'm talking about is the result of cooperation of multiple people, including Dr. O. So his picture is there, right? It's a large team, right? Supported by RGC and ITF, right? So we are with their graduate student, postdoc, and the faculties, right? So we try to work together, right? Try to provide a technology solution to help society, help elderly, eventually help everybody. Okay, then thank you very much.